So in 4.3, you're given this scenario of a relationship between the length of a simple metal pendulum, and that length is measured in meters, as a relationship to the ambient temperature. So physics people, or really anybody, as you heat up a metal, what does it tend to do? It expands, right? It gets bigger. Some of the energy that you put into heat actually makes the rod longer, the pendulum longer. So this is an attempt to relate length to temperature here. And the way that this equation has been given to you, which of these variables looks like it's the dependent quantity here? What's the subject of this equation right now? L. Looks like L is the dependent quantity. So if we were to graph this, we would put the L on the vertical axis and make a little note next to it that L is measured in meters. Now, what's the independent quantity? What's the independent variable in this relationship? What are we relating length to? What story are we telling here? Relating it to temperature. So we're going to make temperature our independent quantity. And again, make a little note next to that with the units. So this, by the way, is good practice whenever you're sketching a graph in science. It's always indicate not only the variable name, but also the units of that variable on the appropriate axis. But what's kind of interesting about this example is that it hasn't been handed to you in the standard y equals mx plus b format, right? It doesn't look like a linear equation. What can we do to the equation that's written here to make it look like y equals mx plus b? Distribute that multiplication, the 1.21 meters, distribute that across the addition on the inside. So let's do that. If we do that, this is going to look more like y equals mx plus b. So L equals, and when I distribute the 1.21 meters, I'm going to move that term to the end here, 1.210 meters. And then I'm going to get 1.210 times alpha times t. Oops. 1.210 times alpha times t. And now we get something that looks a lot more like y equals mx plus b. In particular, what's playing the role of y? L is playing the role of y. And x? T. Those are our independent and dependent variables. We're stuck with those two. But now what's b? The vertical intercept, what's that going to be? 1.210 meters. So there's our intercept, 1.210 meters. And the most interesting of all, what here is playing the role of m, the slope? 1.210 times alpha. So the reason I like this example a lot is that it indicates to us something we're going to need to keep doing this week, and that is when you think of a slope might not be just a single number in an equation. A slope might be made up of multiple numbers or other variables or parameters stuck together. So here, the slope of this equation is not just a single number, 1.210, but it's 1.210 times alpha, which happens to be a parameter. It's a constant. It's called the coefficient of linear expansion of this metal bar, which is going to depend on the material, which particular metal is the bar made out of. But the slope here is 1.210 times alpha. And what units is that slope going to have? What will the units of our slope be here? Don't think it's unitless. Where do the units of a slope come from, remember? Slope is, whatever else it is, a slope is always a rise over a run. And so it's a vertical difference on our graph divided by the corresponding horizontal difference on our graph. So what are the units of the vertical differences on our graph? What are the vertical units here? Meters. What are the units of the horizontal? Degrees Celsius. So what are the units of the slope? Meters divided by degrees Celsius. Well, yeah, so the units of this alpha that you were given here in the problem, the coefficient of linear expansion is given with units of reciprocal degrees Celsius, right? Celsius to the minus 1. But meanwhile, the slope is not just alpha. That Celsius to the minus 1 is in the units of our slope because alpha is a factor in the units of our slope. Where do these meters come from? That 1.210 that's multiplying your alpha, that 1.210 has units of meters. So when we look at this slope, the units of this slope are coming from two different places. They're coming from the 1.210 meters multiplied by the 1.9 times 10 to the minus 5th reciprocal degrees Celsius. But again, we can either see it that way if we know what the slope is, or even more simply, we could have just looked back at the units of our independent variable and the units of our dependent variable and done it from there. The units of our dependent variable were meters, and the units of the independent variable were degrees Celsius. So necessarily, the units of the slope have to be the ratio of those two. So they must be meters divided by degrees Celsius. Always. No matter what else is going on in the problem, if you can think to yourself, what quantities would I be graphing? What variables am I graphing one against the other? As soon as you have an answer to that question, you know what the units of the slope have to be. They're the vertical units divided by the horizontal units. So what we want to do when we come back from break is we've told the story in two different ways now. We've told it using algebra, this first way up here, and we've also kind of told this story in a picture, in a graph. When we come back from the break, we want to talk about this as a story about data, a story about numerical observations. And then from there also to be able to write a story in words, verbal or a written story or something that describes the same kind of situation. So we're going to talk about data when we come back. When data exactly fits a linear model like this one, and when it doesn't quite exactly fit but pretty much fits a linear model, how do we go back and forth between a model equation and a set of data, and then what story is it telling? That'll be encompassed in the H problems. Let's take a half-hour break, and we'll do that right after.